All right, why don't we get started? Why don't you come join us and we'll get started here. Is Tyne, are you ready? Tyne? Tyne? All right, so welcome to GoSF. Glad to see you all here. This is AdRoll, so I want to give a thank you to AdRoll for hosting us. Fantastic space and great food. So round of applause for the folks at AdRoll. And to tell us about AdRoll, we've got Tyne.
Hey everyone, how are you guys doing? Ooh, that sounds like an after work good. Can you say it one more? How are you guys doing? Thank you guys. So my name is Tyne Johnson. I'm a technical sourcer here at AdRoll. AdRoll is one of the, I want to call us the biggest and brightest, but I'm just biased because I work here, but we're a growth marketing platform. How many of you guys have heard of AdRoll? Raise your hand. Yeah? Cool. So we are hiring. So if you are a big data engineer, if you are worked in the back end or Go, you can come and talk to me or my colleague Kamal, who's at the front, and definitely email us your resumes. We also have a ton of product manager positions that are opening up as well. And I believe right now in terms of engineering, we have a big data engineer, a director of solutions engineer position open. We also have a full stack engineer position open as well. So if you guys are interested, you do front and back end, or if you're interested in big data or in solutions, definitely talk to us. And we also may in the future have a Go engineer position available. So definitely talk to me or Kamal. Another thing, a little housekeeping. So our bathrooms are located near our entrance where if you came up the stairs, you'll see a green sign that says bathroom. Also, how many of you guys have LinkedIn downloaded on your phone? How many? Everybody's shaking their head. Yeah? Okay, you guys are still eating. I understand. So if you have LinkedIn on your phone, LinkedIn does a couple of cool things where if you're too busy and you want to connect with someone, if you open up your app right now, like I'm going to do, if you go to where people are adding you, you'll be able to click on the Find Nearby button of your phone. So go to the little people symbol at the bottom, and you'll be able to open up the nearby and then connect with those who have their apps open and add them. So there's a couple of you guys who have your apps open who I could add right now. I've added you. So it's like two of you guys. Okay, it keeps coming in. So definitely connect with those that you may not be able to connect with. Also, if you guys open up your LinkedIn and you see on the search tab, next to it, you'll see like 4 little squares, which will give you a barcode. And that will allow you to scan the other person's barcode. So I have a code, and if you want to connect with me, you'll be able to scan my code and I'll be able to scan your code. Also a reminder, please make sure you sign in. And we have a QR code for sign in. If you didn't, you can also sign in on the laptops. My name is Tyne. Once again, if you have any questions, feel free to come and talk to me and talk to us and get to know AdRoll. Thanks so much.
Let's see if she's available to MC all our meetings. We've got 2 talks tonight. We've got, first one is building Go microservices with Gigi. I'm so sorry, Gigi Safen. And then we've got the second one is Miko from AdRoll, and we'll be talking about processing the event streams at scale. So without further ado, Gigi.
Hi everyone, good evening. Okay, what do I click? Let's see. Perfect. Okay, how many people heard about Go here? Yeah, I have no idea. You always start those presentations with just asking people to raise their hands. I don't know why, maybe so you don't fall asleep. Anyway, today we're going to talk about building microservices with Go using a Gokit. And let's go on to the agenda. So first, who is this guy? Then we'll talk about why Go is a great language for microservices in particular. Then we'll talk a little bit about the Linkshes. So the Linkshes is the demo application that I'm building and will serve as a kind of our foundation for this presentation. And then talk a little bit about Gokit, the framework that we'll use. And finally, there'll be lots of code. So let's get moving. So who is this guy? That's me. Been a software engineer for 24 years, mostly in startups, but also a couple of big companies, Sony PlayStation, probably the biggest one. And then right now I'm the DevOps manager at Helix. Helix is a genomic startup. And if you want to hear more about Helix, then come and talk to me after. And I also wrote a couple of books about Kubernetes, and I'm writing now a book. It's called Hands-on Microservices on Kubernetes. So this talk is really kind of loosely based on the content of the book, and this is just on chapter 3. So now the application is way ahead. And what else? So I'm also a Jiu-Jitsu purple belt. So if you like martial arts grappling, come talk to me too. And let's move on. So why Go? So Go, I think it's an amazing language. Actually, I didn't really like it when I first saw it because it's so simple. It's missing a lot of the bells and whistles you have with other languages. So I came from Python and C++, big languages, C#, that you have all kind of cool things. And the Go is like very primitive. But when I actually started using it, I saw that it's fun to use and it's very productive. And for microservices, some of the biggest benefits is that it's generating a single binary. So it's very easy to deploy. It's kind of what used to be called in the Windows days or those days, Xcopy deploy. Just take the executable, you put it somewhere, and it's all there, statically linked and everything else. The other thing is that for kind of a cloud-native programming, modern programming, it's got excellent concurrency support and networking. Right, so you got kind of the built-in HTTP server and HTTP client. In other languages, it's kind of a third-party library often. And another thing is that Go is really the implementation language for many of the new generation of kind of cloud-native computing, right? So it's a Docker and Kubernetes, lots of data stores like CockroachDB, etcd, and Prometheus, a lot of the components that's kind of part of this distributed ecosystem, they're implemented in Go. So you can say, who cares what language it's implemented in, right? I'm just using it and that's it. But in practice, so probably the best clients, if the server is implemented in Go, probably the best client library will also be in Go. And then if you want to, you need to dive in a little bit to do some troubleshooting, debugging. It helps if the language of your dependencies is also the language that you are most familiar with. And especially Go, which is simple, so it's also easy to troubleshoot and debug. Okay, so microservices. I hope, I won't ask you to raise your hands again, but I hope you know what microservices. But in general, less is more with microservices, right? The systems become bigger, then they become complicated, they kind of start to collapse under their own weight. You need to add a lot of processes and tooling and whatnot. And with microservices, you have this binary boundary between different components. So each one is really simple and easy to work with. And then you got all those nice concepts, contracts, interfaces, APIs that really kind of demarcate the border between different components and helps you to really understand the interaction. So you can consider each simple microservice as a building block that you can test very well and validate and ensure it actually does what it's supposed to do. And then you're going into the next level, which is assembling those and orchestrating those microservices to build an actual system. And then other things, dependencies, versions. So those are things that actually become a little more difficult with microservices because you have more of them, right? When you build a monolith, then everything is internally it's just part of the monolith, and you don't have to worry about different components using different versions of other components. Everything is just in there. And so you need all kind of patterns, specific microservices patterns. For example, your data. Your data is now, it's spread across those microservices. You can do a join. You can do a SQL join across multiple microservices. So you need to deal with it and using all kind of approaches, coming up with things like sagas and CQRS, which is a command query response segregation, and then API gateways to hook up all those microservices and expose them to the outside world. So there is a lot of new things that come with microservices. And then all the normal operational stuff. So logging, tracing, metrics, troubleshooting across multiple microservices could be very challenging. Just keeping track of some requests that flowing through those microservices. And finally, you can utilize a client library. So this is something not specific for microservices, but that's I think that's a good practice that instead of trying to hit the API directly, you can wrap it in client library, which gives you often many benefits. You can hide inside the library all kind of good patterns like retry logic and caching, etc. And there are other approaches to solve it nowadays with proxies and service mesh, etc. But this is outside the scope. And the last thing is Conway's law. So Conway's law, it's about organizations usually build software in the way that are organized. So if you have 3 teams, probably you have 3 subsystems, and those 3 subsystems will be much more cohesive because it's all inside the team. And then when you have things that are cross teams, and you have cross-team communication and processes, and everything is slower. So with microservices, it's often you can have tens or hundreds of or even thousands with big companies of microservices, and not necessarily you have a team on each microservice. So again, how fine-grained are your microservices? That's an open question, but ideally they'll be really small and simple. So how does it work with Conway's law? That's something that each company has to solve for itself. It's not as it used to be. Any questions at this point? Right. So let's talk a little bit about Gokit. So Gokit is a Go microservice framework. And what I really like about it is that it puts a lot of emphasis about the separations of concerns. So I'm coming from, I'm dating myself here, but I started really on the Windows days and the COM components. And I really like this idea of a COM, that you have a binary component. And then you can interact with other components through interfaces. And Gokit makes it very easy to apply this concept of interfaces, and really you keep your abstractions in the right place. So as you see, there are many layers and many things that need to go into a microservice. But if you want to test just one aspect of it or specific aspect, you can do it very easily with Gokit. So it's got this. So it's got few opinions lightly held, which means that it's not just throwing you out there and say, okay, I'll give you just some building blocks and you figure out how to build them. It gives you some guidance, but whenever you want to override something or you have some special requirements, then you can easily do it. It's very extensible, very open, and you don't have to use all the building blocks that sometimes you don't need. So one example is service discovery, right? So Gokit provides you a service discovery through various backends. You can use a console or a Zookeeper or a etcd, but sometimes you don't need it. For example, if you deploy your microservices on Kubernetes, then Kubernetes provides you a much better service discovery. So you just ignore this aspect of Gokit and you can use the parts that you need. So we'll talk more about kind of the conceptual model of Gokit, but pretty much it's built on transports, endpoints, and services. So services, and then later there is also a middleware which adds all the operational aspect that we'll see soon. And it's got, this is something that I really appreciate, it's got built-in transport for HTTP, but also for a gRPC. So that's kind of becoming the new hot trend, to especially for internal microservice communication, where you want your services inside the firewall to talk to each other, where you control both the kind of the services and the servers and the clients. Then gRPC is you get a lot of benefit from it. But often you want to expose outside, you want to expose an HTTP interface just to have the kind of the lowest common denominator. And then Gokit also comes with a lot of support for auth, so both authentication and authorization, and logging, metrics, rate limiting. So he mentioned service discovery, distributed tracing, all the good stuff that you need to really be able to work with microservices at scale. Okay, so that's kind of the Gokit onion diagram. So they refer to it as an onion. It's made of layers. So in the middle, kind of the core is the business logic. So that's actually what we implement as a developer that work with Gokit. We implement the business logic and we expose it through interfaces. And then on top of it, we have service metrics and application logging, which is something, business analytics, which is also often things that we implement ourselves, because this is something that's specific to our application or our service. And then the next layer is operational concerns, right? So load balancing, rate limiting, operational metrics, and things of that sort that we can just benefit from generic Gokit facilities. And then the outer layer are that's the transport. This is how we actually communicate with other services and with the external world. Okay, so that's the link chest. So I think I missed something. Oh, here we go. Yeah, I knew I skipped one. So the link chest, it's a link management and the social graph application. It's just a demo application. It's not serious. It's mostly for demonstrate in the book I'm writing to actually show something hands-on. So don't try to use it. I mean, you can, but don't expect too much. And it's a Delicious wannabe. So if you know Delicious, used to be this link management system that then it got bought a bunch of times by Yahoo and other companies. I think now maybe a Pinboard, I think acquired them last. Anyway, it used to be big in the old days, and they were the first company to introduce the .us suffix. And then a lot of people followed in their steps. So the link just right now, it's got 4 Go microservices. It's got one Python server, which is like API gateway, it does a social login, etc. And then it's got one serverless function to do link checking. And it's using a bunch of data stores. Right now it's Postgres and Redis. And it's also got a Nets message broker for doing distributed messaging and loosely coupled event distribution. So that's the current state and I'm developing it pretty much from week to week. Today we're going to talk about a little more primitive version of it, version 0.1. So you see the link there, it's the 3 and then slash 0.1. I think now it's 0.7, something like that. But there will be plenty to see already. So this is just kind of the graph diagram. So pretty much every user, they send a request to the load balancer, and then it goes through, so that's just a REST API. It goes to the API gateway, and the API gateway can send it to one of those, in this case, 3 microservices. So we have the link service that's responsible for link management, adding, storing links for users. There is the social graph service, which we're going to dive into today. Social graph is about kind of if you can follow other users, you can get notifications when they add new links, etc. Later, maybe chat with them. And there is also the news service, which keeps track of the kind of most popular links and the newest links. And then you can see those things kind of discover interesting new links. Then there is this NAT server, like I mentioned, this is just a event sending. So for loosely coupled, for example, you consider that when a new link is added, then the link service sends a link added event to the NAT server, and then the news service it's subscribed to this event, so it receives this event, and then it does some analysis and decides if it wants to keep this new link or not. All right, so this is the kind of directory structure of this version 0.1. So we have a services directory, and then we have a few services there. Then we have a packages directory, so a smaller font. So you can see each, the idea here is that the implementation of each service is here as a package, just pretty much a library. The logic, the core logic doesn't actually know that it's being deployed as a service or not, so it can run locally or it can run inside the cloud or it can run inside the Docker container. It doesn't really care. This is kind of pure logic. This is the object model, right? So the object model here, we see just interfaces. So the interfaces, they are completely pure Go, right? There is nothing here about HTTP or routing or services or Gokit, just pure Go. Yeah, I have this cool highlight thing, so we can highlight. So this is the service we're going to focus on. So that's its interface, social graph manager. So you can see there is a follow and unfollow and get following and get followers. Those are some of the types. So the object model, part of the object model is the types that are being used in the interfaces, right? So it's pretty much simple structs, and there is nothing special here. So it's using either basic Go types or other types that are defined here, right? So for example, at the bottom there, you can see a get links request. So part of it is links, which is an array of link objects, and the link object is defined there at the top. Pure Go, very easy to work with. And then here we can see this is the implementation of the social graph manager. So this is still in the package, kind of a library. So we have a new social graph manager, and it works with so it's got a store. And what's interesting about it is that the store itself, it implements exactly the same interface. So the store is, it's also a social graph manager. And this is a special case. Usually your store will have a little different interface, but in this case, it's exactly the same. And then we can see here that the implementation, for example, of the follow method, it's doing some kind of very basic checks just to see that the parameters are not empty strings. If they are, then it returns an error. Otherwise, it just kind of forwards everything to the underlying store, and it knows what to do with it. So another, and now here we're going to the service itself, right? So before it was the logic, now this is where Gokit comes into play. So you can see here that we import this HTTP transport from Gokit, and also the Gorilla MOOCs, which is a HTTP router, very good router. And then we also import here the social graph manager itself. So this is the implementation, and then also just the standard net HTTP. And here we see what happens when the service runs. So here we need to initialize everything, right? So the social graph manager, if you remember, it accepts the store as just as an interface. So that helps us in testing. We can pass in like an in-memory store for testing, or we can, if you want to pass it the actual, right? So when it's running, it needs a real data store. In this case, you don't see it here, but actually you can see it here. So it's a Postgres database, right? So this is what the service is doing. It's creating the data store, which is a Postgres database in this case, and this class, the social graph, the social graph store, it knows how to initialize everything, how to create the schema. It's got all everything that it needs to do to handle the storage for a social graph, to store the social graph itself, and then it initializes the social graph object itself, passing in the store. And then there is some other stuff that's not so relevant, pretty much starting the Okay. So then this is the continuation of this run method, right? So now after we created the logic, the core logic, the library that implements the logic, now we need to connect it to the HTTP server. It's an HTTP service in this case. The transport is HTTP. For each endpoint, this is where the endpoints come in. So now we see an example of just one endpoint, right? So this endpoint is the follow follow handler. And what we are passing here is three functions, right? So where you can see it, the make follow endpoint, the decode follow request, and the encode response. So this is a kind of a pattern with Gokit. If you think about it, then each endpoint, it has an input, which is the request, and it's got an output, which is the response, which could include also errors. And then there is something that the endpoint itself, right? We need to connect it to our actual logic to do the work. How it works here. Then still continuing with the run method. So now this is the end. Once we define all our endpoints, then we need to hook it up to the whole kind of HTTP serving machinery. So here we see the HTTP verbs, the methods, and we can see that the handlers that will handle them. And those are the things that we just created here, right? So we created here this follow handler that knows how to get a request, decode it, run it through the real handler, the logic, and convert the result back to an HTTP response. And we hook up everything here. And then the last line is just the normal HTTP. We just start to serve it after we hooked up. So the router, the first line, the MOOCs router, this is the Gorilla MOOCs, which connects those HTTP endpoints to our Gokit service. So here we can see those support functions, right? So it's pretty much getting the HTTP request, and then we want to convert it to a struct because our code works with just its pure Go, right? So we need to kind of, someone needs to translate from the HTTP, from the JSON, or in this case, it's getting the input from the query params, right? So it's getting, splitting the URL and extracting from the query itself the username that we're requesting the following for. So that's following. So the response, so this is nice. Now here we can do something very generic. We just say, okay, the response, we don't care what the response is. We'll just serialize it to JSON, and as long as all the underlying structs that we're using, they are JSON serializable, then this will work. So that's we can reuse it for all the endpoints. We don't have to do something special for each one. Support function. Then there is a so this is the kind of the big one, which is actually we have to generate the endpoint. This is where we hook up everything. So what's a little difficult about it is that we need to kind of traverse this generic world of a Gokit that works with, if you can see the type, so it works with this empty interface, right? The Go empty interface. We need to be able to convert it to something that actually has a strong type. So this is how it's done here. So we have this make get following endpoint, and what it does, it returns a function, right? So its return type is a function which takes those interfaces, and then on line 7, for example, it casts this empty interface to our expected structure. So this is very dangerous. If I pass here the wrong thing, this will just panic and crash. So here I just I wanted to make it a little shorter, but if you can actually check. So there is a way to, if you provide after the result another Boolean variable, kind of let's say on line 7, I could write a rec, comma, OK, and then do this casting from empty interface to strongly type. And then if they don't match, then you'll get a failure, but you don't panic. So your program doesn't crash. And then you can just return a normal HTTP error, and everything will continue. Okay, so Here's an example of how to call. So now our service is running, everything is hooked up, and then we make it. So I'm using here HTTP. If you're not familiar with it, it's like a way better curl for interactive. You see, it provides you a very nice syntax, and the output is color coded. So I really like it as a kind of ad hoc HTTP client on the command line. So here we call the follow method, right? So it's a post. So we do a post and we create here two follow relationships. And you can see that the result, we get back an error, which is empty, which means no error, which is what we expect. And this all happened through the translating and encoding the responses and serializing them to JSON. Then here now, after we added a couple of followers, now we can do a get and call the following method, right? So this is going through the get following Go service, which returns, you can see the on line 9, we get the results, which is a map of following, right? So those are the users that the target user, Gigi, is following, and then we have here two users. And the reason it's a map, right? You can say, okay, why is it a map? Why not just a list of users? So if you have a map, it's very easy to check for a membership, right? If you just return a list and you want to find if a particular user is in this list, in Go, you'll just have to iterate over the whole list. You have to do a for loop. If you return a map, it's very easy to check if someone is there just kind of in one kind of O1 operation. And also in the code, it's less code. Don't have to write a loop. Okay, so that was accessing it through directly through HTTP, which you can do from your code too, right? If you have some JavaScript application and you just want to hit it direct, let's say we expose it to the outside world, then you can definitely hit it through a REST API. But as I mentioned at the beginning, often you want to have a client library, especially if it's multiple microservices, they're talking to each other, all of them are implemented in Go. It's very convenient to have a client library, and then you stay in your service, you stay kind of in the Go world. You don't have to start serializing JSON payloads and think about and check, okay, what's the endpoint, etc. You just get a library with a nice interface. And Gokit helps you to build those client libraries too. So you provide an interface and it looks almost like the server, except everything is the other way around. So now when we encode something, right, so we are the client. When we encode something, we need to encode it from a Go struct, because we're working with Go, so we have a Go struct. And since we need to send it to an HTTP, so we need to encode it into a JSON library. So that's the encode. So now we encode the requests, and the response, it's the other way around. The response that we will get back, or that the client will get back, it will get back a JSON response from the HTTP service, from the REST API, and then it will decode it back into a nice Go struct. That's what we see here. And this is what it looks like. So it's pretty much what I just described, right? So we're getting a body, we're getting now the response that we get is an HTTP response. You can see on line 6, and then on line 11, we just use JSON, and we use the decoder. So we decode the JSON into the response that object that we expect, right? Which is in this case on line 10, we define here the response. It's the get following response, which is pretty much a Go struct with this map of following users. Then on line 15, we can see the actual implementation of the get following. So this is kind of the business logic of the client. So it's making the call to the endpoint. It's creating the request, right? So the request in this case is just the username. Or we ask, okay, who are the users that this user is following? And we're passing this to the get following endpoint function. And then we get back the response, and it's already got decoded along the way. So this is what the Gokit is taking care of. But since it's generic, again, it returns. You can see again on line 6, you can see that the return type is just an empty interface. So in our get following method, on line 21, we need to, again, do the casting. And again, I'm doing something that's unsafe here. I'm just assuming that everything works. And if there was an error, so this is the case where we need to translate errors too, right? So if there was an error, then it will be in the payload, in the inside the response struct. And what we'll do here, we'll convert it. Now we're converting it to a Go error, right? So on line 23, we create a new error, and we just pass in the text of the error from the struct. And then finally, we return either the response, we return always the response dot following, which is the map, and then also the error. That if there was no error, then it will be nil. But if it was, then it will contain the text. And then there is much more to Gokit and to services in general. So there are all kind of concerns that I didn't touch on here. So how do you do unit testing? How do you do end-to-end testing? The data stores. So we talked about it a little bit, but I didn't really show you how you can, using interfaces, quickly switch between them and utilize different data stores, and even completely switch from, let's say you start with a relational database, and then you realize that actually a key value store is good enough. You don't really need something more sophisticated. So you can really change things under the covers. And then error handling, it's much more than just returning errors. There's all kind of, you want to do retries, maybe you want to report something, you need to log some errors, you need to even ignore in some cases. Logging metrics, all the operational concerns. How do you build, how do you deploy those microservices? Versioning, tons of stuff that comes with the territory. That's it. Any questions? Yeah, just a second. Yeah, okay. All right, I'll repeat it.
But looking at your example, it looks like that there's a lot of boilerplate code here. Is that how Gokit works in general, or is there a way to reduce the amount of boilerplate, or is that something that needs to be done in the project? Because it looks like there's a lot of extra code that you have to write to connect all the bits and pieces together.
Right, yeah, that's an excellent question. So the question was if all this extra boilerplate code that you need to write, if it's something that Gokit promotes, or if it's just something that I did in this project. So this is something that definitely it seems like you can easily generate this code. It's very repetitive. There is nothing really custom about it. There's no reason for you to write it. So there are a couple of projects to generate this code. And I was thinking about it too, and I think that the best way to do it is we didn't really focus on it in this presentation, but if your interfaces in the signature you have multiple parameters, then it becomes a little more. You need to do some work to translate. But if your inputs are always just one struct, let's say you have 3 parameters, right? So for example, in this case, if you want to follow another user. So you need to say, okay, who is the followed user and who is the follower? So you need 2 parameters. But if you put it in just a struct and you always call it something like a follow request, and the follow request you have in there, then you have just one struct, and it's very easy to generate it in a way that you don't have to do anything special.
I guess I mean the code where you generate all the servers and all that, extra boilerplate. Could you use Reflect or something where you name things in a certain convention and it kind of, works out what needs to be connected, or use configuration or something like that instead of writing code?
Yes, so you can definitely do that, and there are a couple of ways to do it. So a reflection is a great way if you want to really explore your kind of dive deep and drill down into your interfaces and your data types. So you can just generate the whole thing. And other approaches is basically mentioned on a convention. So you can always have some naming convention, and then you can always take it from there. But at some point, you need custom code. So in case of, for example, if it's really a JSON HTTP, then you can just use the standard serialization. If it's something like a gRPC, then you'll need something that you can use the Google the protobuf tools to generate it too. But yeah, definitely I think this is the right approach. Here I wanted to show specifically what's happening. I didn't want just to show some magic and say, okay, here you call this, and believe me, there is a service underneath that does everything. But for a production, for large scale, yeah, I think definitely you want to have to generate all the boilerplate. So kind of I had a couple of times that I made some mistakes, and it was really difficult. So kind of I had a point. I tried to serialize a pointer to a struct instead of the struct itself, or vice versa, and it was yeah, pretty painful to figure it out. Okay.
I was wondering if Gokit is looking to solve any of the tracing issues associated with microservices. Like user enters X, it goes to system A, goes to service B, it fans out, it goes to SQL, it goes this, it goes there, and then something fails, and all you see in the log is that something panicked.
Yeah, so Gokit definitely wants to help you with that. So it supports ZipKit, and it's got the whole middleware for distributed tracing. So it definitely addresses it. So you don't, again, it's all optional. You don't have to use it, but it's there. So you have all the batteries, and you choose if you want to use it or not. Maybe you have another solution, so you don't want to, but if you don't, yes, you get it from Gokit.
More questions?
You say that Gokit can be added on top of gRPC. What would be the real advantage of using Gokit on top of gRPC, knowing that gRPC already gives you client generation and the entire, like even server code generation? It generates a lot of the boilerplate for you, and a lot of the tracing, like OpenCensus, by default support gRPC. So you also get that almost for free. What's the real advantage of using Gokit with gRPC?
Right. So I think the advantage is that when you use a gRPC without any wrappers on top of it, then you have to deal with the whole type system of the protobuf. You have to import all kind of libraries. There are all kind of restrictions there. When you're using it through Gokit, you have the option. It's the separation of concerns is much better. So the underlying, yeah, you get the strong typing, right? You get the client generation. That's great, but it feels, I think, a little more heavy-handed when you use gRPC directly. Okay, thank you.
Great. So we got Miko, Jula. Oh, here you are. All right. I've got some waters here.
Hey, how are you doing? How are you doing? I'm going to talk today about this thing called, it's on the slide, it says Baker, a Go project that we torture a lot by putting a whole lot of data through it. So as an introduction, the way you pronounce my name is Mikko Juola. I've been with AdRoll for about 3 years. The things I do with AdRoll, they're usually like around data pipelines. Like some common pattern is that, okay, we're forming a new team. The team must build product X that will be on the dashboard and show a bunch of numbers. How do we get the data for that and compute them efficiently? That's the kind of theme, the things that I work around on. And one of the big tools I use is this Baker thing that I'm going to tell you all about. So what's going to be on here? So many of the Go projects that you may hear about, they're like, okay, let's make this HTTP service, real-time API or something like this. This may be one example of a Go project that's almost completely we're just going to push a whole lot of data through it and see how fast it goes. So I will show an architecture, how that works, and some like key examples, how we actually manipulate, configure this thing. And the second thing is that since it's a complicated project, one of the good things we had in Baker is that we made it as least intimidating as possible to new Go programmers. AdRoll is not really a Go company. We mostly write Python and Erlang. So it's important that if we're going to have a common project for a lot of people, they'll be able to easily extend this thing. So I will show some pointers how you can make things a little less complicated. And finally, like I just said, since this is a pretty good fit for a Go project for this data processing, I kind of want to show how it's better than some of these other solutions for this kind of thing. So these three things are the things I will talk to you about. So first, some context. It'll be easier to explain what is the purpose of Baker if you first understand like what kind of data we actually process. So if you didn't figure it out from the name, we do marketing. And one of the big things is internet advertising. So when you do a lot of advertising, you're going to end up with a whole lot of data, a lot more than you can fit on your laptop. Well, unless you have, I've seen these YouTube videos where people put water cooling on their laptops. So if someone came to me and said, okay, Mikko, we made this laptop. It has 1 petabyte of hard drive on it. I would not immediately think of it as a lie, but I would be a little skeptical. So, but the point is, this is not the kind of data you can do on just one computer. So as for the data itself, it's basically, if we talk about the formal model, it's a stream of events. So if you're not familiar with like this advertising terminology, when you go on the internet and maybe you see like a banner ad somewhere, when that happens, we call it an impression event. And when it happens, we make a record. Okay, this dude just see an impression on this website. At this time, the ad was this, and so on. We make a record of all kinds of information when that happened. And some people, maybe they click on them, and then another event happens, we make a record, and so on. This is how we can later on analyze the data, what exactly happened with our advertising campaigns. So what is the tangible format of all of this is, it's just CSV files. So one line in the CSV is one event that contains all the information we need. If I list them, they just look like this. We compress them with the Z standard, but the point I'm making here is that the data that we have is not much more complicated than just a pile of CSV files. And this is what Baker also processes. So getting into what is the whole purpose of this thing, we get in all these log lines, Baker will take them, it will run a bunch of code on that, and based on that, it will write some output in some format somewhere. This sounds very abstract. It's because Baker is very configurable, so I will get into the gritty details. But first, what kind of things is this useful for? So for one thing, these CSV files that I showed you, all of that data is unorganized, and Baker can organize it. What this means in practice is that, let's say I work in reporting team, and I need to count how many impressions happen on this one specific customer. If I take those CSV files, I'm going to have to scan all of them. There's so many of them. And like I said, the super laptop with 1 petabyte doesn't exist. So things are going to get a little difficult. So one thing we do, and what is the most important use case of Baker, is that we can turn that into some kind of other format that's much more suitable to doing these kinds of queries. This is the most important thing. But the second thing is that not only can Baker turn these things into other formats, it can also sanitize them in some way. Like we may have different data sources and they may not be compatible with each other. We can use Baker to fill out like missing fields, or if some data looks bad, we can drop it or something like this. Filters are a pretty good feature of Baker, which I'll talk about in more detail. But finally, since this is a common need that AdRollers need, our whole data kind of revolves around these event types. We call them logline data. So we made this Baker very modular, very configurable. And since Go is easy to learn, it's easy to extend it. So this is very useful. But then, how does this thing actually then work? Like, what is it doing? I'll first show you what is the data flow architecture. It's not very complicated. If you look at it, we have these events, those CSV files I was talking about. They go on the top to the input module, they go through a bunch of filters, and finally, they come out of the output module, which produces processed data. This may seem very abstract. It's input, filters, output. If you get down to it, almost any software can be described like this. So I'll give them some actual names. So starting from the top, S3 input. If you're not familiar with what S3 is, it's like an Amazon file storage service. If you have files on your computer, you can upload them to S3. The file will stay there, and you can later download it back. That's what S3 is, basically. So when I have S3 input, what this means from Baker's perspective is that I'm telling Baker, hey, please download all those CSV files from S3. And then once it downloads them, you can do things with them. In our list of filters, I have examples of fraud filter, timestamp sanitizer, test impression filter. These are like business-specific things you can do. And finally, when everything is done, we can output it to some file format. In this case, my example is TrailB, one of the formats we use to actually store event data. But the whole thing here is that all these components, they're interchangeable independently. So if I don't like S3 for some reason, I can decide that, okay, please, Baker, let's pick the TCP input instead. This will make Baker open like a local port that, hey, you can connect to this and push all the log lines through that instead. Or you can use Kinesis, another Amazon service, where you can get this event data in real time. You can choose inputs independently, you can choose what filters you want, and you can choose your output module, SQLite, CSV, same format as what was the input, and so on. But the way you configure this is one of the things we tried to make simple. So I have two here. I have the data flow diagram, and I have a configuration file over here. And the one thing I want you to notice is that the configuration file has roughly the same structure as the data flow diagram. So input, I decide, okay, that's S3. The files are in this location in S3. And then I have all these filters. Please, Baker, process my data this way. And finally, output, where do you want to put all the resulting data? It's easy to teach engineers that I'm introducing to Baker how this works when the configuration and the way the data actually flows is pretty much the same. And finally, since Baker, it's just a command line tool. So you build it, and then you point it to your configuration file, and poof, Baker is going to do its thing. It's very good. I want to get into more detail for these filters. How do you write them? Because it's one of the parts that we tried to make as easy to write as possible for engineers who don't understand Baker as a whole. So what filters can do, they can drop lines, they can manipulate lines. When I say lines, I mean events coming in. We usually call them lines or log lines since they're located in log lines. So whenever I say log line, it's the same as event. So different engineering teams, whatever products they're trying to make, they can encode some business rules, like something like a reporting team that computes impressions may add their own specific stuff in this filter. So filters can be specific to some team or very specific purpose, but some of them are general purpose. And I think the best example is the fraud filter. Nobody wants to deal with fraudulent traffic after all. And now I've been talking for like 10 minutes in a Go meetup, and there has not been any Go code. So let's fix that. So I want to show how do you write a filter. The point here is to show how little code there is after all. So let's pick this apart, starting from the top. Step one, you need to define some kind of structure that defines what stuff your filter needs in order to do whatever it needs to do. The fraud filter is a good example because it's easy to explain. If you're ever, or if you know about advertising industry, fraud is a big problem. There's these robots on the internet who just click on the ads, they're totally crazy. So one way to combat this is to maintain a blacklist of IP addresses where you've seen this kind of clicky behavior. And that address list, you can load it inside Baker, inside the structure, and that will be used to filter out this bad traffic. So that's step one. You need to define some structure for this. And step two, you define how do you want to create one instance of this filter. It's not very complicated. This skeleton here, for the fraud filter, we get these IP addresses from somewhere. This function, load blacklisted addresses, It's not specified here. But you load them, and then you return an instance of your fraud filter. If you look at what this function is supposed to return, API.BakerFilter and error, that Baker filter is an interface that specifies what things the filters need to implement, which is not much more than the process function, which is this next one. This is where things get a bit more interesting. So this is the function where you have to actually process the log lines in some way. It takes two arguments. The first one is this L letter. It's type API log line. This is the event. It contains all the information about maybe impression happened here, then, and then. But the second argument is this next function. That's where things get interesting. So if you look at this body of this code we have here, does this line look like fraud? If it does not, then we call next. What next does is it sends control over to the next filter. I'll have another example of that very soon. But you can put this all together, and this is basically the skeleton you need to do. It's very easy to teach to new engineers since there's not a lot of code they need to do. But if you're being totally honest, you still have to write tests, metrics, and so on. So there's about 20 more steps. But we're going to ignore you have to do that, so let's move on. So going back to this data flow diagram, I've omitted the input this time. There are 4 filter timestamp sanitizer, timestamp sanitizer, difficult word, test impression filter, and the output. So if I put this together, this is like a snippet that I had. Have the process function from the fraud filter, sanitize timestamp, and the test impression thing. So the Baker framework will chain all of these together. And finally, the last filter will send the line to the output, which will then output it to something, or it does not. We have an output that doesn't do anything. Sometimes you just want to run a bunch of filters. But that's how it works. And this is the big point. So in the few years that we've been using Baker, I've seen that this thing is simple enough that Go writers, or people who have not written Go before, they've been able to write new useful filters by looking at other simple examples. And there's a good benefit in here. When we have a simple, like, common code base for AdRollers who need to process log lines, everyone gets the benefits of these complicated general purpose filters. Like the fraud filter is a good example. It's like 1,000 times more complicated than I showed on the slides, but it's easy to explain. But point is, everyone can use these good generic filters, and we don't have to duplicate work for any team. That was the filter story, but I want to talk a bit about the performance. How did we make this thing fast? And there are some techniques that we did. So the base framework, when I say base framework, I'm meaning like, let's ignore all the filters, outputs, any details about them. The base framework that will glue together all these filters and outputs, that part itself has been heavily optimized to make sure we do things as fast as possible. So one of the key techniques is that we don't do any allocations in this base framework. So one technique is, when we have these API.logline structures, these are the things that we feed to filters, and they manipulate these things. We use this sync.pool module. It comes with Go. It's not some exciting external library. We create this pool, we put all those log lines in there, and whenever we're getting a new line from whatever input we have, we get this structure from the pool, we send it to the filter chain, and then we finally put the log line pack to the line pool. If this code is hard to follow, there's a pretty darn good documentation of this thing on the sync pool module in the official Go website. So if you want to learn more about this technique, that's where you should go. And the other thing, the filter chains. This is a bit extended example from what I already showed you. So we have the process function for the fraud filter, takes the log lines and so on, and it calls the next function. So it doesn't directly go to the next filter, but we still wanted to make the glue between filters as small as possible. So there's only this tiny function between them at runtime before we go to the next filter. Oh, and if you don't call next function, the line is dropped. That's how fraud filter can drop lines. As for like actual real-world performance, I'd say about 120,000 events can be done per second on a 16-core machine. I ran a little benchmark with this SQLite output, meaning that we put all the resulting lines in an SQLite file. One event is around 3 kilobytes, so if you want to turn this into how much actual data there was, looks like it's around 400 megabytes per second. And this is with all the production filters, like what we usually use in real time. I think we have about a dozen filters in most pipelines that use Baker minimum. So this is a real world example, it's not some toy example. That's around the real world performance. So I have one final point to make. We're back again at the data flow diagram. Well, here's one thing. I actually lied. This is not how it works. Or I should maybe say I did not tell the whole truth. The actual thing looks like this. We want to use all resources on a server that we can. So most of our servers have 16 CPUs or something like this. So we spawn one Go routine. We make multiple instances of filter chains, and each of them runs in one Go routine. And when we get input logline data from this input module, we send those events to different filter chains to make sure we use as many resources as possible on a server. Got to utilize all the things. Amazon servers cost a lot of money. And then there's the one thing. We don't run Baker on just one server. We have about, at peak times, a few hundred of them. But that is a pretty complicated topic on its own. And it's not really Go related. The whole orchestration system is not in Go at all. So we usually use this MapReduce-like pattern. But since it's so complicated, I will not tell you more about it. Sorry. What to take out? So in my opinion, the best things that Go had for us, it's easy to learn, or gentle learning curve, saying it really nicely, and it's performant. Many of the other languages, Python, for example, it's easy to learn, but you could not make as performant system with it as you could with Go. So I think this is a pretty good niche. The Go is pretty performant. When you don't do any allocations or this kind of stuff, you can push quite a lot of data through it. And since the extensions, we made sure that they're simple to write. We were able to build the system that performs pretty well, while at the same time, all these people who don't know Go that well are able to extend it for their own purposes. So this worked out really well. I don't think it could have been done this well in any other language. And I think that's actually all I had to say. So thank you for listening. I suppose we'll now take questions.
Hi, thank you. I found the Baker system very similar to Apache Flume. I don't know whether you heard of that, which is written in Java. I don't know whether is that, because you mentioned the performance is a big gain using Go in Baker. I wonder, do you have any comparison with Flume?
So I don't have exact performance to anything else but I know that some similar projects do exist, but not that work exactly the same. So it's kind of hard for me to say over that. Baker itself, Baker is not open source, by the way. So if you go try Googling it, you're not going to find anything. But we're working on open sourcing it. It still has a lot of AdRoll lessons in it. But if we do that, it would make pretty good compare. Like at that point, we could compare it pretty well with other projects. Yeah.
Thanks for your talk, Mikko. It looks like when using round robin to distribute your log lines across all your Go routines, does that mean that each filter doesn't have its own state? So for example, look at an impression and then correlate that information with a click, for example. And does that screw you up, or is that why you've got the funny merge thing at the end?
So this is, I think, one of the weaknesses of the system. So you technically can write a filter that will, like, instead of calling do I have the code anywhere close by? Over here. So you can just not call the next function and instead store the log line inside the filter in some state. But in practice, since the filter chain works like this, you have multiple of them. And if we talk about real world, we also have a whole lot of servers that do this. In practice, it's not going to actually work for many real world use cases. So the answer is that filters typically need to assume that they cannot look back into any event that happened. They have to work on like the same log line. The fraud is a pretty good example, since sometimes you can't tell a robot except from like counting how many clicks they do. So some of the things you can't actually do with Baker, but for most, like, it still is a very useful system. So.
Can I ask a related question?
Yes.
If you're not storing any state, is that why it's easy for filter writers to avoid allocations? Because you talked about using your pool. What makes it easy for filter writers to avoid allocations?
Nothing. It's more like some filter writers actually, like it depends on who writes the filter. If you want to be careful, let's not allocate anything, then you will play nice and don't do any allocations in the filter. When we talk about actual filters that we have written, some of them are very inefficient. They were maybe written out by a person who did not go that well. And others, like this fraud filter, for example, have been heavily optimized to make sure they run efficiently. So it depends on like who wrote the filter and what kind of diligence they had in making sure allocations don't happen. But Baker itself doesn't really help in that.
Yes, I have a question. Thank you for presenting this. Pretty cool. The question I have is, if I heard you correctly, you said each event is a CSV file. Is that correct? And if that's so, why is that?
Like okay, CSV file is the common format that we have, but technically Baker does not have to use CSV as long as like if you talk about the modules that you write over here, the purpose of the input module is to take whatever input source you have and convert it into let's go to the code again. You see the API.logline which stores it. It usually is CSV, but it technically does not need to be, as long as it's some kind of input source that you can turn in the structure. But it just so happens historically AdRoll has had CSVs for a very long time, so that's how it works.
I see. Okay, that was my question. Thank you.
You talked about the fact that you're using all the resources available on a specific server. Have you guys explored the ability to distribute the work across multiple servers? And if you have, what are the bottlenecks that you guys encountered, and why is it that you chose not to do distributed?
We do have distributed. So the way this thing works is that, okay, a little complicated to explain. That's why I said I was not going to explain it on this slide. But
that's fine.
No, I will explain anyway. You asked me. So we have an S3 bucket which has a whole lot of these log lines. Like let's say there's 100 terabytes of them. We have this program that counts that, okay, one server can process 1 terabyte in half an hour. And we use that to like split the work that, okay, this server, please take this 1 terabyte of lines and process them. This server, please take this other terabyte and process them. We automatically like provision servers from Amazon, calling this spot market, and then run them, and then they write the results back to S3. If you talk about bottlenecks, the bottleneck is usually like in real world applications has been the output module. Some of the outputs that we have, you just can't write data to them fast enough. So everything else is kind of bottlenecked on that. Just know what the real world bottlenecks have been. Yeah.
Yes. So there are a number of tools in this space. What are the influences that you took from the prior art, and how do you see Baker as improving on them?
I have no idea, because I didn't write this originally. So we had this precursor project at AdRoll that was a lot like Baker. It was written in C, Lua, and mistakes. So we kind of fixed it for Baker. But as for like if there's any kind of like similar project that this was inspired on, I'm not actually aware of them. There may have been something, but I was not there when it was first made, so.
How painful is it to add a new input module or output module?
Can you repeat the question?
How painful is it to add an input module or an output module?
They're a little more complicated than filters, but not too much. The interface you have to write is a bit more complicated. Outputs are a bit easier than inputs. Like almost all use cases actually use the S3 input, so a lot of people don't have exposure on them. The filters are by far the easiest to write. For outputs, they support things like, okay, we want to shard the data once it comes out, so we don't write just one file. We actually write like maybe 100 files. So if you look at this, let's go here. There's multiple instances of the output module here as well, and they may be writing to different files. So that part it gets more complicated. It depends on like whoever writes the output. They don't need to support, for example, this use case, but the effect is that you cannot then run this thing efficiently. So inputs and outputs, more complicated, but not too much. Oh yeah, so if you look at the, yeah, we have this configuration file over here, just like you said, but the filters themselves, let's go over here, look at the process function. They do not need to know what the next filter is. The Baker, like the base framework, if we call it that, kind of chains together these next lines. So when you call it, it will go whatever we configure it to be the next. Filters are typically designed to not depend on what the next filter is. It's just like a complete independent package most of the time. So. Yes. Yes, okay, so I don't have code for that, but there is this thing inside Baker that will make like this. Okay, I have a small example. Let's go back over here. If you look at the middle one, this is like a little part of code where we chain together all the filters in like, we make this closure that calls the next filter. It's hard to explain because I don't have the full code here, but we have this little loop that will go through all the filters that have been defined, makes little closure functions that chains them together and passes the next function correctly. So we do have a thing like that, but it's just kind of hard to explain with what I have here. So that depends. For example, the fraud filter didn't always exist, but when we realized that huge number of clicks are fraudulent, we kind of, okay, we have to really write this filter. Right now, it's not that often that we need to write new filters. It's often these days is that new team picks it up and it has to make some very team specific filter. So we don't do like general purpose filters anymore. It's not that often anymore. Maybe like once a month someone writes a new filter for Baker, but it's not used by everyone, only by one specific team.
One more question. If you have enough time and enough resources, will you port Erlang part of your software or your company to Go?
Can you repeat?
Yeah. If you have enough resources, will you port Erlang part to Go? In other words, can Erlang do something which Go cannot?
If I have enough resources.
So will you port Erlang to Go?
Oh, I think we actually have. Like some of the parts that were in Erlang are actually in Baker now. So we have ported some parts of Erlang into Go, but we have other projects that are more suited to Erlang, in my opinion. But it's kind of like we use the best tool for the job. And for this one, Go is the best tool.
Still, Erlang is best for some other job.
Yes, like for example, the ad servers that get a whole lot of like requests in, we use Erlang for that. I think it's more suitable for that kind of thing. For Go, I think it's surprisingly good for this kind of data processing. I don't see these kind of use cases that often, but yeah.
Just one quick question. How do you retain the order of events in the output?
Depends on the output module that we do. We run Baker typically just for one day, so we know that all the events that come in are going to be on a single day, but there is no guarantee they'll be in any kind of real order. So one of the things that Baker do, I think I mentioned it, it organizes the data, and one of the purpose of that is to put them in time order. So another application that kind of consumes whatever curly bees SQLites we have can then use the ordered data. So Baker is the one that actually puts them in order.
This is after the filtering of the filters.
Yeah, it's typically the job of the output module that makes the output file. Sometimes it's inherent to the output file format. That curly bee that I mentioned, maybe not heard of it, it specifically has to have all events in time order. So just by using that file format, they automatically, everything goes in order.
Do filters like filtering out like only part of the event message, or only the events that pass all filters gets written into?
Do you mean like if events themselves like specify what filters?
No, when you run a filter on a message, does it filters out only the portion of your event message? Is that what the filters are doing?
Depends on the filter. They can manipulate them freely. They can drop them. They can also duplicate events if they want. So they can kind of do anything, whatever the filter's purpose is.
Okay. Do filters depend on each other's like output? That's why they're chained as a sequential.
Yeah, like all the filters, how we write them, they're all independent packages. So when you put in a filter, it doesn't depend on what other filters are in the pipeline. You technically can write like filters that expect that other filter does this thing. But in practice, we've avoided actually writing such filters because we want to keep them as like independent packages.
Why is it in sequential order instead of like, can you do parallel?
It's let's go over here. So sequential order, well, it's simple. Basically, that's all the reason there is. We could theoretically like extend Baker that, hey, let's have this complicated filter chain. But since most use cases work pretty well just with this simple filter chain, then we've decided, okay, we'll go with this one. Easy to explain, easy to use, very performant.
Thank you.
Hi. Hi, right here. Thank you. So I actually have a follow-on to that question, which is very similar. I'm not sure if I caught the full answer. So if I understood correctly, is the sequence of filters, each of the filters acting on the same log line? And by that, I mean the original log line, or are they passing a potentially mutated log line through?
Okay, let's go to, where are we? Not this one. Let's go back. Okay, this is a good point. So, okay, it looks like I stubbed out one of the arguments, but yeah, the filters, like it depends on the order which you specified the filters in the configuration file. So in this case, if my fraud filter decides to drop the line, the other filters are not going to see it because we never passed it. But some filters, like let's say the sanitized timestamp, it never drops lines. It sanitizes the timestamp in the file. The next filter would see that modified line, so they only get the input from the filter in the previous step.
I see. So a follow-on to that, I'm imagining there are complications around between filters. You kind of have to know what the new interface is, meaning like if a previous filter mutated the data, you need to know exactly what the new format is going to be.
In practice, this usually is not actually a problem. Like I said, the actual filters that we have typically don't depend, like they don't have hard dependencies on each other. There are some use cases, like I think we have one where they have like a hard, I expect this filters to write this and then this, but they're kind of rare. Like we specifically avoid writing that kind of code. And then there's the also thing, like one of the reasons Baker is not open source is that the schema of these things is totally fixed. Like events have these specific fields and so on. So filters typically can expect that fields mean the same thing. There's not any funny business going on. Makes it easier to write like consistent, independent filters.
I see. So they're basically field boundaries that's baked into the schema.
Yes.
Okay, thank you.
Can you stick around for a few more minutes?
Sure.
Awesome, great. So round of applause for Miko. At AdRoll. All right, so our next meetup is going to be May 22nd. I think story of Go at Uber. And we got an open slot. So I need speakers both for May, June, July, August. So if you want to speak, please send me a note. Anything, speak on anything related to Go that's of interest. Great talks tonight. Let's get some more talks. All right, thank you.
Can